Right. I think, I start now. Hi, good morning, everybody. And thank you for coming to this web seminar that today will be on data assimilation. And my name is Carla Cardinali, and I'm leading the section of data assimilation that I will introduce shortly now. So this web seminar is part of a series of seminars organized by CMCC. That is a foundation with the goal and the strategy to create the really health simulator for climate and for longer range weather forecast. But it's not only, the idea to create a simulator. I mean, the mission is not only the health simulator, but actually also to help in the climate, during the climate change for adaptation and sustainability in our society. So CMCC is basically a foundation across Italy. So it has a collaboration and with 6 different universities and 2 institutes, Italian institutes. And that is quite a nice idea because it's not in one place in Italy, but it's spread across Italy. So creating, in a way, giving the possibility to different institutes to communicate for one goal. So lots has been achieved in terms of computational resources. So now we are Lecce, we are 2 different computers, and with some map the capability of these 2 computers, we have 25,000 cores and a velocity, a peak performance that is to 2,400 terabytes. So it's fantastic facilities, and that is spread among, the different division at CMCC. That counts about 11 divisions, and in particular, this division is the climate simulation and prediction is the division where data simulations, coupled data simulation is sitting on it. And so the system data simulation, that is an activity very young that has been created 3 years ago at CMCC. And initially it was just me, and unfortunately Giovanni, that is presenting now, joined quite soon after. And in 3 years from scratch, we have created a lot of activity in data simulation. So from the infrastructure necessary to really organize and follow any experiment we are submitting. So we have a proper model from an open source that is running now, an atmosphere data simulation spread that is running now or quasi operational. And we are working to transform, to couple this atmosphere with the land and with the ocean. And we have been developed lots of amazing tools, diagnostic tools, that can be used in climate, in seasonal forecasts, longer range forecasts, and based on a data simulation system. And we are collaborating with different institutes across the world. And we are really in development with an EU project. So Giovanni will tell you about part of these activities that we have initiated and we are now developing. And so I give to Giovanni the words. He will present the seminar will be on advancing in data simulation, the methodology, the application, and the diagnostics.
Thanks, Carla, for the introduction, and thanks to all the participants. So given the the flavor of the seminar, I need to briefly introduce myself. So I will give at the beginning a really short my background in a nutshell, and then we can start off fun with data simulation achievement that we are getting here from the theory to application and diagnostics. So my education is a bit heterogeneous in the sense that I have a bachelor degree in physics, and the bachelor thesis was about statistical mechanics, in particular on GPU computing, so simulation, Monte Carlo simulation, statistical Monte Carlo simulation using GPU computing. And then I get a theoretical physics degree. I got a theoretical physics degree on specialization in general relativity. And then the PhD here in Bologna, actually among Bologna and Ca' Foscari, in under the supervision of Antonio Navarra and Joe Tripia, using some tools like path integral, Fokker Planck equation, transition probability matrices in order to understand the climate dynamics. In particular, we concentrate a lot on ENSO, trying to look at the ENSO as a system that is able to jump between two different states and to explain the asymmetry in its probability distribution, and then started to use some transition probability matrices to understand the forecast of ENSO. Then I spent 3 years and a half in Hamburg studying chaotic advection and introducing hyperbolic covariant covariant structure to unveil hidden structures in fluid dynamics, and then move on turbulence in geophysics, starting, for example, to understand the dynamics from the velocity statistics, and introducing a statistical measure and selective decay principle for generalized Euler dynamics. And finally, I came back here in Bologna, and thanks to Silvio Gualdi and Benassi, Mariana started to work again on ENSO and its modulation by PDO. And I start with Carla the work on data assimilation. Here I will present data assimilation, as I said, in 3 different perspectives, 3 different flavors. Let's start with the methodology, in particular talking about the physical nudging. So all the main schemes of data assimilation can be derived, can be based basically after some assumption on this relation, the bias theorem, in which we have PA, our prior distribution, that, for example, in ensemble common filter is a Gaussian, in which the covariance matrix is computed exploiting the ensemble. In a variational method, it's a Gaussian in which we precompute the covariance matrix, and then we have a likelihood function in which we have the probability to have the observation given our states. Then, multiplying this to probability, we are able to find, for example, in the Kalman filter approach, our analysis and our covariance matrix. In the variational problem, if the nonlinear operator are considered, we need to consider this product in terms of variation, so maximizing, for example, this probability. Then we have also a particle filter that basically assume that we have an ensemble, and this ensemble is weighted by some weight that are derived by the likelihood function. So all the main schemes of data assimilation can be based basically on this theorem after some assumption. The point is that this means that all these schemes are completely derived by a statistical process, and they provide really interesting and reliable results. In fact, we are able to progress in the analysis and then in the climate study. But my point is, since nature observation represents nature and the model represents an approximation of the nature, maybe we can use some other perspective to approach data assimilation. Maybe we can use a statistical mechanical mathematical framework to derive a DA scheme. And maybe we can formulate DA as a dynamical boundary problem, for example. So for this reason, I'll start to consider another data assimilation scheme that is nudging or Newtonian relaxation. It's really old, and what we do here is considering our dynamical system. So x here is our state vectors, and f of x is our also nonlinear dynamics of our system, and then we apply to this system a new term that is basically the difference between the observation y at the forecast time, at the analysis time, and the simulated observation. So h is an operator that brings our state vectors, compute the simulated observation, and then we do a comparison. And we weight this quantity with this gain matrix that in this case is basically a diagonal matrix, which diagonal elements are just 1 over some time scale. So it's really easy to implement. And it's used nowadays in many applications. The point is that it's totally empirical. And in several books, you also find some sentences like nudging method gives suboptimal results, in the sense that it does not satisfy any minimum error criterion, for example. But I mean, we know that from a physical perspective point of view, the variational principles are present everywhere in physics. For example, we have the minimization of energy. We need to minimize an action to find the trajectory of our system. But we don't need to have something that minimizes some error, for example, the variance, unless under some particular circumstances, for example, if everything is Gaussian. Otherwise, we need something that minimizes all the moments of a distribution. So why don't introduce more dynamics, more physics in, and maybe we can derive this system physically, and we can try to check, to understand also the other dynamical system schemes in terms of statistical physics. And we can see where maybe we can try to correct maybe better that schemes. So it is legitimate to ask, is there a physical framework that allows for the theoretical derivation of the nudging equation? And further, what happens if, for example, we introduce unresolved processes in our dynamical system? And why we can assume that the adjustment of the trajectory toward the observation is correct, just because we correct the system close to the observation or at the observational time. So we need to understand better if we also want to increase the statistic that we want to use in our analysis. And at the beginning, I started to find this first solution to the problem using an approach that I will describe below. So we found that introducing these relaxation terms plus a correction, a constant terms, that the dynamics computed at the observational time, xf, we can correct our system without introducing other parameters. But the point is that this equation, first of all, must be intended in a discretized framework because it's derived by a stochastic differential equation. And further, we do not have two really important ingredients of data assimilation that are the information from the backgrounds and the observational error covariance matrix. So how can we introduce these elements? So here, the sketch of the workflow for the derivation. We need to exploit the connection between the Langevin equation and the Fokker Planck equation. So we have a deterministic problem, our dynamical system. And then we add some noise to parameterize unresolved scale dynamics, for example. And then we transform the deterministic problem in a stochastic problem, still in the state evolution space, okay, in the coordinate space. Then we can exploit the connection, the bridge between the Langevin and the Fokker Planck equation that describe the evolution of the probability of this system. And we can formulate here in this new space the D8 problem. And then once we get the appropriate formulation, the appropriate Fokker Planck equation or its substitution, we can then try to get back and determine the deterministic system. So let's start with this procedure just sketched. Let's consider a dynamical system by component. So xi is the component of our system, and fi is the nonlinear dynamic that governs the evolution of this component that depends by actually by the whole system x, and we add some noise. This nu represents some fluctuation, and I is the modulation of this fluctuation for this component. Now, the fluctuation, just to take the problem easy, is Gaussian and white, so mean is 0 and correlation is delta in time. This omega actually could be absorbed in this modulation. And since our approach is, let's find first the correct equation that transport the system toward the observation, let's consider at the beginning that all the components of the system are observed. Then when we have the equation, the system of equation, we try to understand how to approximate this system in order to address the real world. So the a world in which we do not know all the system, but we can observe just partially the system. And again, from this Langevin equation, we can directly read the corresponding Fokker Planck equation, so the evolution of the probability, because the nonlinear dynamic has a drift of the probability, and from the modulation of the noise, we are able to read the diffusion of the probability. So this is what is used also in some text of data assimilation to introduce some ensemble filtering, for example. The point is that we have some initial condition, our analysis, and we see the forecast during the forecast, the probability that spread along the phase space. And then we need to complete the information using the likelihood function of the bias theorem. I don't want to use it. I want to use dynamics information. So we do not need just this P, but we need another piece of information, this Q, that tell us that from a certain time, a certain position, we can go toward the observation. This is the probability to go toward the observation. So we are not interested in this P here, but in this equation 8, actually, in the product of these two probability. But this means that if we want to transform the D8 problem in a boundary problem, or we use an equation with second order time derivatives, or we add another equation and take care of the second boundary. And maybe we can try to merge the solution in the original Fokker Planck equation. And this is the approach that I'm going to follow. And the equation for the second probability we are interested in is the Kolmogorov backward. So just the adjoint of the Fokker Planck equation that can be written in this way, in small time approximation. And the final condition is exactly the distribution of the observation. So here we include the information of the observation, while G contain the information of the backgrounds. So this is how we can introduce these two information in the game. And if we do the computation, actually, we are able to find out a single equation, a Fokker Planck equation, that it looks like the one that they just showed, but with a new terms, a potential that include information on the observations. So actually, it corrects the trajectory of the probability. And from this one, we can go back in the coordinate space. So, and we can read directly from this equation the modified nudging equation, but this time is not empirical, it's derived. So we have our system plus this potential here. Now, this is really interesting, but the point is that the results are quite formal. And also using a low-order model, it makes difficult the computation of this probability function. So what can we do? We cannot stop right here. So using, as I mentioned above, the small time approximation. So we know that, for example, this Q can be written in terms of path integral. We can try to solve in a sort of Taylor expansion in time the solution. And if we do that at first order, we end up with equation 12. That is actually a more practical form and an equation from which we can learn a lot. Because you see, we didn't use the bias theorem, but we get a correction that actually looks like the correction for other of the other data simulation scheme. In fact, you have a gain matrix that it's really similar to the one that you have in variational DA or in some common filter, but there's a new correction. Why? Because in our case, G is a rate of the covariance matrix. And in fact, is multiplied by this weight, this time. Usually in a sum of common filter or in variation of divar, for example, this weight doesn't exist. And if we do know a few things on the background covariance matrix, and we also assume that it's varying, but varying slowly, we know also less about its rate, but then we can assume that is more constant. So maybe it could be also easier to be modeled. And that's also another thing. These terms that in Kalman filter and 3D bar act continuously, here actually at the observational time, here we have a continuing correction, but the backgrounds act when we are far away from the observation. When we get closer to the observation, only R remains. And also for in the innovation part, you see, you have XF, that is our observation, minus our system. And this is the usual innovation terms. But then when we are far away from the observation, we also have this new correction. So this is a way to see data simulation in another way and to continuously correct our system. And then just to test the feasibility of this problem, I used a surface quasi-geometry model, so a model by Elden 95, starting with a lead peak initial condition, and in the control run, after sometimes we get this vortex. Fine. If we perturb the initial condition, we end up with a complete different states. Consider that the grid is 128 times 128, so the covariance matrix is more than 16,000 points, contains more than 16,000 points. So we need to apply some localization procedure in order to implement our system. And we also need to approximate this term here, because at the observational time, if we, like in this example, we consider only 30% or 10% of the domain observed, we can consider here the observation that we have and the other component as a sort of average of the system along the last assimilation windows, just to have an estimate of this order correction. And actually, what's happened, if we applied the old physical nudging, we are able to remove the backgrounds, but we get a vortex that is not smooth at all. while with the new nudging, we are able to find a vortex that is much smoother, and this can be seen better in the transition. This is the control run, this is the perturbed run without data assimilation, and this is what's happened with the old physical nudging. So you see all these dots because we wanted to go toward the observation without knowing anything about the local surrounding. And so we correct punctually the domain, generating some noise, while in this case, in the new formulation, we are able to get a smoother initial condition, a smoother transition. So this is about the first part, about this methodology, but methodology can continue with the next part here, also called application, because it's much more practical and is about what Carla just mentioned at the beginning, at the introduction. And this is a work done by Carla, me, Gustavo de Goncalves, Sami Sarinen, and Marcello Guattura, and Zopan Malik. In particular, the aim of this part is a transition from a really good research data simulation tool that is DART, based on ensemble adjustment command filter, and transform this tool in a scalable, fully parallelized air data simulation system, a quasi-operational system that is called here spreads. We introduce here a spatial and temporal forward operator, similar to the FGAT, so first guess at appropriate time, in order to get better correction during the simulation, in particular for the radiances. And then we introduce also a flexible and dynamical query language databases to handle millions of observations. So instead of text file, for example, and we can then manage more observation, and we can start to work also on a weakly coupled DA system. In particular, now we are concentrating on atmosphere and land. And how this system is working. So in order to implement the FGAT procedure, we consider an evolution of our model, the CSM, and for example, from 6 to 12, and we consider 6-hour assimilation windows. In these assimilation windows, every 30 minutes, we write the output of the model. And in this way, we are able to divide our assimilation windows in 13 time slots. Now, starting from a huge database of observation in buffer from the CNWF that include 500 million observations, we go for blind thinning in order to reduce the number of observations that we need to handle. And then we transform the observation we use in SQLite databases. These databases are then divided in smaller chunks, and several chunks can belong to different time slots. Then, if the time slot have different chunks of observation, and we have a different backgrounds for every time slot, we compare the observation of every time slot with the corresponding backgrounds in order to compute the innovation. And then, after we computed all this prior, we put the results in one database, and we continue the algorithm with the standard ensemble adjustment command filter to correct the central backgrounds. This is how spreads work. So divided in 3 phases. Phase 0, evolution of the model. Phase 1, computation of the prior of the innovation. And then the regression, the regression with the phase 2. Which observation we are assimilating? Brightness temperature from different platform, satellite platform from Aqua, NOAA, METOP. When I talk about brightness temperature, I mean L1B product. so georeferentiated, but not retrieved product. And then we also assimilate the atmospheric motion vector, radio occultation, and then also observations that are derived by other sources, for example, aircraft, radio zones, and buoys, like the temperature profile of specific humidity and profile of U and V component. Just a quick profiling. On our machine, we saw that phase 0, so the evolution of the model, work in this way. Using 2 nodes per member, we are using 80 members at the moment, and half-degree resolution, and 83 level vertical resolution. 1 member takes 15 minutes. With half nodes, 34 minutes for the evolution. The phase 1, here 18 minutes, all the 13 time slot, but actually this can improve to 10, 12 minutes, because it doesn't matter if 1 time slot, maybe with less nodes, take more times, but we are able to do in batch simultaneously more time slot, and so in 12 minutes we can finish the phase 1. And then phase 2, the heaviest one, it takes less than 1 hour with 25 nodes and managing a database with 10 millions of observation and 80 members. Clearly, along all the simulation, we need to monitor the assimilation itself, the full fields, differences with other reanalysis, for example, ERA 5. We need to check and monitor the increments in different regions, how they behave along the assimilation cycles. And so we develop a diagnostic tool, a browser, that allow us to monitor completely from model space to op space all the assimilation in an easy way. So we can handle hundreds of plots for all the different cycle and different assimilated variable in an easy way. And in order to facilitate the analysis, the data assimilation procedure, we translated our scripts for spreads in EasyFlow. So in this way, we have tools, graphical tools, that allow us to follow all the chain of the assimilation from the phase 0, 1, and 2, and we can monitor where the system is stuck, if everything is going okay, if we need to resubmit something in an easier way. But then we also need, beside the common diagnostic, to understand also if our forecast is improving or not. And we need to do this in the most objective way we can. So we need to introduce an objective forecast sensitivity to observation impact for an ensemble system, a general ensemble system, not tailored for just one specific algorithm. And because we know that more observation means a better analysis, clearly, unless you are using really bad observation with huge errors and completely biased. But generally, more observation means better analysis. But how much these observations are able to reduce the error in the forecast? Because the forecast error depends on different factors. For example, the leverage the observation have in the analysis, the use of the correct observation accuracies, biases in the model and model errors, limited numbers of members. We can use 80 members, but we know that in order to remove, for example, spurious correlation, we need to increase really a lot the number of the ensemble member. So we need to introduce something that measure the variation of some error. And in fact, what we do is introducing this vector E. That is nothing more than the difference between the observation at the forecast time and the average of the simulated observation at the forecast time. So we have our ensemble of forecast. We compute the observation, the simulated observation from each member, and we take an average, and we do the difference. And then we build this objective const function. So that is basically an error. This is the square of this quantity here that I just mentioned. And it's weighted not with a norm that depends on analysis, depends on the model, but it's weighted with the sigma O, so the error of the observation, to be more objective, as more objective as possible. This has been these quantities introduced by Carla and then Cardinali, and then we use this objective function. And we also want to not only understand if the forecast is degrading or is improving, but as I will show you, we'll try to connect this quantity to another interesting and important quantity, the observation influence. Now, step by step. Now we have this error, this const function, objective const function. Okay, now let's take the first variation in terms of the analysis, because this X here, this forecast, is nothing more than the model applied to initial condition, to our analysis. So we can take the variation. When this delta J is larger than 0, it means that we are degrading our forecast, while if it's less than 0, we are doing a good job. The point is that the variation with respect to the analysis translates in these sensitivity gradients, that it's really hard to compute. But we have an ensemble. And then if we consider, for example, 6-hour forecast, 1-day forecast, we can try to assume, as hypothesis, that the simulated observation are linearly related with our initial condition. So you have basically a scatter plot of simulated observation and analysis, and you can get the coefficient of this relation. If you want to go behind this time scale, you need to consider a polynomial expansion. But for the idea, this is more than fine for the moment. And actually, you do not neither needs of this alpha coefficient, but just the second one. That include the correlation and the spreads of the forecast and the spreads of the analysis. If you plug this relation inside the sensitivity gradients, you can find an easy and clear solution of our problem, because the variation now is given in terms of this correlation and in terms of the spreads of our ensemble and by these innovation vectors. Okay, so the first variation in this formulation depends on the sensitivity gradients of the models, on the observation error, on the simulated observation. And when we get delta J be larger than 0, synonymous of forecast degradation. Less than 0, synonymous of forecast improvement. And to suppose linear relation, we need to consider a short forecast. Otherwise, we need to extend the range with polynomial relation. But the point is that now, with that relation that can be easily computed with all the variable stored during the assimilation, we can try to build several important information, because we can try to collect the pieces of this variation that we need in order to create bar plots or maps of the impact of some particular observation. Here, an example of a prototype in which we explore several types of observation, and also divided by Northern Hemisphere, tropics, and Southern Hemisphere, in which we can see in this example the impact of the satellite, that it's much larger than all the other conventional observation. Clearly, can be also make more complex this plot, including the by category, by type, the one that improved or the one that degraded the forecast. And then we can also look at maps, for example, in which we can see slices of the SWOT, in this case of a particular satellite at 50 hectopascal, channel 10 for AMSU of the platform method one. And you can see where it's degraded the forecast blue, or degraded the forecast red, or improved the forecast in blue. This was just a prototype. Actually, you need to consider a large mean, statistical mean, in order to really understand where the model is failing, or our data assimilation is failing or not. But the point is that with this formulation now for ensemble filter, we can also relate this quantity to another really important quantity, the observation influence. Because if you remember, our variation was written in terms of the spread of the forecast. But now we know that the observation influence at time 0, so the analysis, it's related to the spread of the forecast at time 0 and the observation error. So we can try to connect this quantity to our forecast spread. How? The forecast spread will be proportional to the initial spread, because it will increase, increasing exponentially using a Lyapunov exponent of the system in some way, right? So it will be proportional. For sure, for every type of observation, we will have a different constant, but doesn't change the rationale behind. So if we substitute then this relation in the original formula, and we consider the connection of the spread at time 0 with the observation influence, we have a connection between our objective forecast impact with the observational influence. And then we see we can relate these two important quantities. And we can see that when the observation influence increases a lot, so the observation play a really important role, this doesn't mean that the forecast necessarily will be improved. Because if the correlation, because of the model, because some bias and bad feedback, because some bug in our simulation system is negative, then we will get a positive delta J. And the more the observation influence increase, the more the degradation will be highlighted. So just to conclude and summarize everything, from the methodology perspective, I show how to derive a set of nudging equations starting from a statistical physics point of view. Using a small time approximation, we can find a practical expression for the nudging equation. And with this equation, we describe the DA as a boundary problem. And from the application, we can see that we modify our research DA tool to obtain a quasi-operational one, also introducing an FCAT approach in our workflow. We can manage millions of observation, that means SQLite databases, that allow to easily assimilate several satellite platforms. And we introduce several tools to simplify the validation and the production of the analysis. From the diagnostic perspective, in parallel, we develop another important tool for ensemble filtering based on objective function to understand the degradation or the improvement of a forecast. And we related this sensitivity for quantity to the observation influence. So what we can do next? Well, using the new framework for the methodology, so the physical nudging, we can use this new scheme on more complicated and realistic system. And we can also consider to approach a sort of strong coupling assimilation, because it's easy, can be easily introduced, and we can explore, for example, variation, the correction to the SST, for example, given by the lower part of the atmosphere or vice versa. And from the diagnostic point of view, from the application, we need to improve the profiling and the scalability, but we are already at the point. And from the diagnostic point of view, we can try to get longer diagnostic and implement also in an easy way the relation that I showed you before, and start to use variation of this quantity to understand the impact for example, for other quantities in another interesting project that involve the land, for example, series, because they can use also for diagnostic, not just for data assimilation, but with small variation, also for the climate understanding directly. So thank you for the attention, and please, if you have some question, I'll be glad to answer.
Thank you very much, Giovanni. It's very interesting seminar. You touch on lots of many different topics in the data assimilation subject.
Thanks,
right. I would like to know if anybody would like to ask a question to Giovanni. Okay, so in the meantime, I like to ask a question about, on the last tools you presented on this sensitivity to observation impact. Of course, I mean, what you presented is based on the linear assumption, okay? So then, for example, for this respect, I mean, this tool has been used in the past and then is going to be used straight away now in our system for, let's say, diagnose the impact, the one day forecast impact, results. And so would you see any way, considering the new approach that you just, the solution, okay, that you just presented, would you see a way in which, the range of forecasts that we can, let's say, diagnose, I mean, exploit and then look at could be longer than just one day forecast?
Yes, Carla, thanks for the question. I thought about this, and I think it's feasible. And the rationale behind is exactly the same. The only things that we need to change is the relation, the linear relation that we use to approximate the simulated observation and analysis. Instead of using a linear relation, we need to expand and consider a second, third, fourth order polynomial, let's say, in the scatter plot. And then we can proceed exactly in the same way. So the relation at the end will be more complicated, and maybe the connection to the observation influence will be less clear than now. I need to check. I didn't do that for the moment, but yes, it's totally feasible, just with a slight different change.
Great, thanks. Is there any other question from the audience? I think, yeah, probably. This is the second time we went to this seminar, so we had a lot of questions the first time, so probably now people feel more comfortable for what you have presented and less questions are coming. And right, so if there are not any other questions, I would actually then close this seminar now. I would thank again all the participants, and thank you very much, Giovanni, for the very nice presentation.
Thank you too. Thank you all the participants.
Great. So see you for the next web seminar then, all of you.
Bye.
Thank you.
Thank you.
Bye.